Hello everyone, today we'll be learning about known metals. In the previous class, you have learned that there are very few known metals as compared to metals. Some of the examples of known metals are carbon, sulfur, iodine, oxygen, hydrogen, etc. The known metals are either solids or gases except bromine, which is a liquid. So the known metals are in the form of solid, are in the state of solid or gas, but there is one exception, bromine. This is in the form of a liquid. Do known metals also have physical properties similar to that of metals? Let's find out. Collect samples of carbon, coal or graphite, sulfur and iodine. Carry out the activities 3.1 to 3.6 with these known metals and record your observations. Compile your observations regarding metals and known metals in table 3.1. So, on the basis of the observations recorded in table 3.1, discuss the general physical properties of metals and known metals in the class. So here we will just discuss the various physical properties of known metals. So all metals except mercury exist as solids at room temperature. So mercury is a metal, but it does not exist in the solid form in room temperature. It has a very low melting point. But gallium and cesium have very low melting point. These two metals will melt if you keep them on your palm. So they will melt even if you keep them on your palm right here. They will just start melting. Iodine is a known metal, but it is lustrous. Now these are all the exceptions that are written in metals and known metals. So iodine is a known metal. It means metals are supposed to be lustrous and known metals are not. But iodine is a known metal. Still it is lustrous. Carbon is a known metal that can exist in different forms. Each form is called an allotrope. Diamond, an allotrope of carbon, is the hardest natural substance. Now, known metals are supposed to be soft and metals are supposed to be hard. But a diamond, which is an allotrope of carbon, that is a known metal, is the hardest substance known. So here, basically, a known metal is very, very hard. In fact, harder than almost all the metals. And graphite, another allotrope of carbon, is a conductor of electricity too. Known metals are supposed to be insulators of electricity, but here a known metal is shown to be conductor of electricity. Alkali metals are so soft that they can be cut with a knife. Now metals are also supposed to be hard, but alkali metals like lithium, sodium, potassium, they are very soft that they can even be easily cut with a knife. Elements can be more clearly classified as metals and non-metals on the basis of their chemical properties. As we see that there are a lot of exceptions in the physical properties between metals and non-metals. So we will look at some other factors to distinguish them with each other, and these are the chemical properties. So take a magnesium ribbon and some sulfur powder. Burn the magnesium ribbon, collect the ashes formed, and dissolve them in water. Test the resultant solution with both red and blue litmus paper. Is the product formed on burning magnesium acidic or basic? Now burn sulfur powder. Place a test tube over the burning sulfur to collect the fumes produced. Add some water to the above test tube and shake. Test this solution with blue and litmus paper. Is the product formed on burning sulfur acidic or basic? So most known metals produce acidic oxides. Okay, these are two things that you need to remember. So known metals, so you can just remember them by opposite. That known metals should have been basic, they should be soft and basic and easy, like right that. So but it's opposite. They produce harder, acidic, harmful substances. Known metals are supposed to be soft and unharmful and squishy type, right? But they in fact produce acidic, that are the opposite of soft and all that. So known metals produce acidic oxides when they are dissolved in water. And metals produce basic oxides when dissolved in water. So you can just remember it by that they produce opposite of their nature. Known metals are supposed to be soft, but they produce harder or rougher substances like acidic oxides. Metals are supposed to be harder and rough, but they produce softer and basic substances like basic oxides. Right? You can remember them in this way, that they produce their opposite nature. Known metals, so acidic. Metals, so basic. Known metals, they were supposed to be producing basic, but they produce acidic. And metals are supposed to produce acidic, but they produce basic. Right? So that's how you can easily remember it too. Now chemical properties of metals. So now we will be discussing in this video, I think we'll just cover the chemical properties of metals only. And maybe even that won't be fully covered. Let's start. We will learn about the chemical properties of metal in the following sections. What happens when metals are burnt in air? Now we'll be looking at their chemical properties. When we burn something, a chemical reaction takes place in it, right? You have seen in activity 3.8 that magnesium burns in air with a dazzling white flame. Do all metals react in the same manner? Let us check by performing the following activity. So you can read this activity on your own, right? This is just for a kind of example so you can understand it easily. Almost all metals combine with oxygen to form metal oxide, and then the formation of metal oxide is also the reason why metals rust, right? They react with oxygen in the air, and that is why they also rust. And since almost all metals rust, we can clearly say that all metals combine with oxygen to form metal oxides, right? Metal plus oxygen is equal to metal oxide. That is, oxide means the reaction from the oxygen present in air. For example, when copper is heated in air, it combines with oxygen to form copper 2 oxide, a black oxide, right? So 2Cu means 2 into copper, 2 times the copper atoms, plus O2 oxygen, it will form 2CuO, copper oxide, copper 2 oxide. Similarly, aluminium also forms aluminium oxide. So aluminium plus oxide, aluminium oxide, iron plus oxygen, iron oxide, copper plus oxygen, copper oxide. So metal plus oxygen is metal oxide. So just write the name of the metal here, then oxygen would be right here as it is, and then write the name of the metal and come and write oxide in the end. That's it. So you can put any metal here and the name and put the same metal in this side also, right? So here it could be iron, then it would become iron oxide. Oxide and oxygen will remain the same. If it's copper, then the copper oxide, ferric oxide, and stuff. So recall from chapter 2 how copper oxide reacts with hydrochloric acid. We have learned that metal oxides are basic in nature. Okay, metal oxides, their opposite, basic in nature. But some metal oxides such as aluminium oxide, zinc oxide, etc. show both acidic as well as basic behavior. Now this again, here is an exception. Like exceptions exist everywhere. Such metal oxides which react with both acids as well as bases to produce salt and water are known as amphoteric oxides. You need to remember this word, amphoteric. It's similar to amphibians, right? Amphibians can travel in both water and land. So that's why they react with both acid and base. So amphoteric oxides. And what do the reaction between an acid and a base produce? It produces salt plus water. Now this is aluminium oxide plus hydrochloric acid. Aluminium oxide means a metallic oxide, metal oxide plus acid. And what will it form? It will form aluminium chloride plus water. What is aluminium chloride? It's nothing but salt, right? Salt. So we have learned previously that metal oxides, or let me show you just so you can remember it easily. What happens, acid or base? Here it is. How do acid, reaction of metallic oxides and acids? Here we had read it in this is chapter 2. In the chapter 2 we have read how metal oxides react with acids to form salt and water, right? This is metal oxide plus acid and it will form salt and water. And on the other hand, the reaction of a non-metallic oxide with a base will also form salt and water, the same reaction. So this is what they're doing here. This is a metallic oxide, this is a metal oxide, this is an acid and it is forming salt plus water. Then aluminium oxide plus sodium hydroxide. Sodium hydroxide is a base. Then again it will form what? Sodium aluminate plus hydrogen, plus H2O, water. So it is again forming salt plus water. Most metal oxides are insoluble in water, but some of these dissolved in water to form alkalis. Okay. Sodium oxide and potassium oxide dissolved in water to produce alkalis as follows. You can just see the reaction from here. It's nothing important. Not too important. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Like I told you previously, potassium and sodium especially, are very, very reactive. Like if you drop a bar of sodium into water, it will just start combusting. Okay. So now to protect them from reacting, they are kept immersed in kerosene oil. Kerosene forms a kind of film, covers a form of envelope all over it, so that it doesn't react with the outside surface, right? Forms a kind of blanket. So at ordinary temperature, the surface of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxide, right, with the oxygen. So the uppermost layer of metal reacts with oxygen and forms a layer of metal oxides in the just the outside of the layer, just the outermost layer. Let me give you an example. Right, I'll give you an example. So this is a bar of metal, let's say, right, and then there is obviously oxygen present all over outside. So this oxygen present here reacted with this much of say metal, and it formed this thick sheet of metal oxide on the metal bar all around it, right? This one. So this area is basically metal oxide, this area is a metal oxide, and under it is the actual pure metal, right? I think this is very obvious, no need to teach in detail. So layer prevents the metal from obviously from further oxidation. Iron does not burn on heating, but iron fillings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black color layer of copper oxide. You must have seen that when you try to burn something, kind of a very black sheet forms over it, and black flames also start coming out, and like when you burn something against the wall also gets covered in a black film into kind of black soot, right? It's SOOT suit, not SUIT suit. So it gets converted into kind of black soot. So that is your oxide. Okay, that is the reaction with the oxygen. Silver and gold do not react with oxygen even at high temperature. That is why their color does not fade, does not change, even though they are kept outside, or they are burned, or whatever is done to them. They do not change their color. Like that kind of black soot would not form on a piece of gold. Anodizing is a process of forming a thick oxide layer of aluminium. Aluminium develops a thin oxide layer when exposed to air. This aluminium oxide coat makes it resistant to further corrosion. Okay, this makes it resistant to further corrosion. So sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. So this is nothing but what I have told previously, that sodium is the most reactive metal. We will put the next parts in the other videos, because this video is getting a bit big, right, in size. Okay, so see ya.